Hello everyone, my name is Aaron Standard. I'm the founder and CEO of Petabridge, and today I want to talk to you about a feature we've recently added to Akka.net called Akka.Delivery, which is a reliable point-to-point message delivery system that is able to essentially guarantee that messages are delivered in the original order they were sent to a receiver over the network. And the system also provides message chunking, so the ability to take really large messages and break them up into smaller ones in order to avoid head-of-line blocking. So we're going to go ahead and kind of cover some of the delivery defaults and outstanding issues in Akka.net today as far as message delivery is concerned. And then we'll talk a bit about how Akka.Delivery addresses some of those problems in a really hands-off, fairly automated and robust fashion. We'll go ahead and include a little code sample to talk a bit about exactly how that works in practice today as well. Let's start by going over deliverability modes. So what are the different, let's say, types of guarantees that might exist when we're trying to deliver messages over a network? Well, the weakest guarantee is at most once delivery, otherwise known as fire and forget. And this is weak because messages might be lost. There's no one on the sender or the receiver side trying to keep track of in-flight messages. Next, we have at least once delivery, which is a stronger guarantee. And this usually requires the sender to keep track of all messages it's previously tried to send, and typically requires the receiver to explicitly acknowledge that it has processed each individual message that's been sent. The problems that at least once delivery has is message duplication. It's possible for the receiver to receive the same message multiple times. And it's also possible that messages might be delivered out of order. So for instance, if a sender delivers 3 messages, the receiver fails to receive the first one, but receives the second one and acknowledges it. And then there's a third message that might be queued up. The sender might deliver that third message before the first message is redelivered. So there's all sorts of different potential consistency issues you can run into there. And then the next strongest guarantee is exactly once delivery. Now, there really isn't such a thing as exactly once delivery. It's really at least once delivery with duplicate detection and the ability to enforce ordering on the receiver. So it requires state to be present on both ends of the wire. This is the most expensive form of delivery, but it does tend to be the most consistent and ultimately provides the strongest guarantees for client applications. Akka.net defaults to at most once delivery. And the reasons why we do that are that it's stateless, so it doesn't require the sender or the receiver to keep track, which makes it very inexpensive. It's not uncommon for users to have potentially millions of Akka.net actors all running inside the same process. If each one had to keep track of all the messages it was sending at any given time, that would be prohibitively expensive from a memory consumption standpoint. So that's one reason why we chose it. Another is that it's fast because it only requires traffic to flow in one direction. So there's no bi-directional communication here. And then on top of that, for in-memory processing with Akka.net, you don't typically need anything stronger than at most once delivery. The reason being is that the only scenario where you could potentially lose a message would be an actor restart, in which case the only message you might lose is the one that caused you to throw an exception. And you actually have a chance to handle that in the pre-restart method. And if you want to learn more about that, you should check out our video on how actors restart. I'll link to it above. So basically, long story short, for in-process messaging, one-way messaging is good enough. Now, when you start going over the network, we know that the network is unreliable and that it is a matter of when, not if, a failure occurs. Therefore, at most once delivery is vulnerable to message loss going over the network. So typically you have to implement retries or maybe a library like Poly to go ahead and implement exponential backoff, whatever the case may be. We typically want a stronger guarantee for some of our messages going over the network. The other distributed systems problem that at most once delivery is susceptible to is rather than just, let's say, a routine network failure like congestion or maybe a network error of some type, it's also vulnerable to process crashes and restarts. So in the event that, let's say, a sender is delivering messages to a consumer and that consumer process crashes, all those in-flight messages will be lost by default. Conversely, if the producer crashes, any messages it was trying in the middle of producing and trying to send will also be lost. Akka.Delivery helps address both of these types of problems, and we'll learn a bit more about that in a minute. The other messaging issue that affects sort of normal Akka.net today is our message serialization and encoding system. Typically, Akka.Remote, our transport layer for moving bytes from one actor system to another when we're operating in sort of a distributed system is a single TCP connection between those nodes. You as the Akka.NET developer don't typically need to worry about where an actor reference is when you're sending it a message. If it's an actor co-located in the same process as you, you'll just send an in-memory copy of that C# class or object or struct or record, whatever the type might be. Whereas if you're going over the network, we're going to recognize that this message is being sent to a remote actor. We're going to route it to the actors that own that particular TCP connection. And then we're going to serialize that message. We're going to turn it into a byte array. And then we encode the bytes that we produce during serialization using a technique called frame length encoding. Those messages get queued into the TCP byte stream, which then get received on the other side of the network. The frame length encoder basically figures out how many real messages are inside the buffer. I'm going to show you an example of that in the next slide. Deserializes those messages and then routes it to your actor. This is what frame length encoding looks like, and this is what Akka.NET uses by default. There's several different encoding schemes that TCP systems use. Frame length is very common. It's also possible to use things like delimiter-based encoding, and maybe there's some other techniques out there. So if we have a 16-byte array, we might have a 1-byte header that basically explains how long this message is, how many bytes past this header is this message. And this is how we take an arbitrary array of bytes that are delivered to us by the operating system level sort of memory and socket handlers and figure out how many messages specific to our application are actually stored inside that byte array. So this is what the encoding process is for. And so in this case, we've got 1-byte header, we'll throw that away. We'll take these 4 bytes, deserialize it. Got another 1-byte header, throw that away. We have a 5-byte message, we'll deserialize that. Then we have a 3-byte message, and in this case, we have a free byte that we're not using. Head-of-line blocking is a problem where you try to send a really large message over the network, and it basically occupies all or most of the buffer space. And by default, in Akka.Remote, we only allocate 256K of buffer space on the read and write side, so 512 kilobits per connection total. That value is configurable. So let's suppose we transmit a message that's 128 kilobits in size, so that's roughly half the buffer space. Any message that we want to deliver concurrently while that one is currently being written to the network is going to have to wait behind the 128 kilobit message. And that message is going to have to be completely received, processed, and deserialized by the remote end of the network before any of those other messages can get through. So as a result, these head-of-line blocking issues can create timeouts. They can go ahead and cause network instability if the message is large enough, and the larger you make your buffer sizes and your max message sizes, the greater that amount of latency can become. Akka.Delivery can ultimately help us solve this problem, and that's what we're going to go ahead and learn about on the next slide. So what does Akka.Delivery do? Well, first, it's a point-to-point delivery system, which means that as soon as a message is produced, the producer is going to try to route it to the consumer. So it's basically kind of a real-time delivery system. It is reliable and optionally durable. This means that we automatically sequence messages. We maintain a buffer of messages that have not been acknowledged by the consumer. And we also can optionally persist that buffer so that in the event that the producer crashes and restarts, we can pick up exactly where we left off with no message loss. Message order is preserved, crucially. So the system will go ahead and order messages using sequence numbers. And those sequence numbers will be preserved on both the producer and the consumer side of the relationship. One thing we've also experimented with here is that this is a strongly typed messaging protocol. So we haven't been able to type actor references yet. That is a feature we have planned. But we've typed the actual, let's say, creation of the actors that are involved here. And we also expect you to use, let's say, grouped messaging protocols, where essentially you take all the messages that belong to a particular domain, and they should all be organized under a common interface. That's a very familiar and routine pattern in Akka.NET. Finally, point-to-point delivery also supports back pressure support and the ability to chunk large messages. So back pressure support is crucial. If you haven't watched our video on how back pressure works, you should definitely check that out. But what back pressure support allows us to do is tell a producer that's moving way faster than a consumer that it needs to slow down in order to prevent the system from tipping over. If we didn't have any sort of back pressure support built into reliable delivery, what could end up happening is the buffer size could just grow infinitely, even if there's no consumer on the other side of the network. And as a result, your delivery process would eventually run out of memory and crash and basically become unusable. So the back pressure support is actually built in to keep the system safe, and it does a very good job at doing that. Chunking support for large messages is how we solve our head-of-line blocking problem. This is basically the ability to take the serialized representation of one of your messages. So before we send it over Akka.Remote, we serialize it inside our producer actors and chop them up into fixed size chunks. And that means that in between each of those chunks, other messages from other actors can go through, so we don't have head of line blocking anymore. We're able to kind of concurrently allow messaging from multiple actors and also this big message to get delivered over the network. At some point in the future, we might implement pull-based delivery. That is not something we currently have planned, although there is a specification for it. And this is a instance where it's rather than the producer essentially forcing messages towards the consumer pulls messages at its own sort of self-determined rate from a producer that just buffers them. We don't have that implemented yet, but when we do, we'll go ahead and add a link to that right here in this video. So this is sort of what the actors look like that are involved in Akka.Delivery. There's a producer and a consumer. These are your user-defined actors, and they do have to implement a messaging protocol that's built in as part of Akka.Delivery. We'll show that to you in our code sample. But the actors that do most of the heavy lifting are actors that are built into the Akka.Delivery system. This is the producer controller and the consumer controller. And these actors are both typed. They'll only handle messages that are sent to them that implement type T. So basically they have a generic constraint. The producer controller is really kind of the brains of the operation. It's responsible for basically maintaining a globally unique producer ID. I'm going to warn you now, if you have multiple producers that all have the same ID, this system will not work well, and do not bother filing a GitHub issue. You do not read the documentation. The reason why the producer ID has to be unique is this is how the consumer controller is able to determine if the sequence messages it's receiving are in the right order. If it sees that the producer ID is different than the one that it's been working with previously, it's going to throw an error and dump those messages. So you need to have a unique producer ID. It works the same way that an Akka.Persistence ID does. It's used to kind of globally identify a unique instance. So I'll go ahead and show you an example of how we generate unique producer IDs per node using a little bit of consistent hashing, which I also have a video on that right here if you want to learn more about it. But we're going to go ahead and use that to basically generate unique per node producers inside our system. The next thing that the producer controller does is it automatically sequences and optionally chunks all messages that are delivered to it via the producer. This is basically how we go ahead and get ordering handled inside this Akka.Delivery system. Is the sequence numbers determine the order in which the messages were originally produced, and therefore this is also the order in which those messages must be processed by the consumer. And Akka.Delivery will do its best to enforce that. We have the consumer controller system. The consumer controller is the actor that works on the other side of the network. It basically is responsible for handling deduplication of messages. It's responsible for letting the producer controller know how far through the delivery buffer we are. And it kind of really sets the rate for overall message consumption speed inside the system. The other thing that the consumer controller does is it forces the consumer to explicitly acknowledge each of the messages it's produced. And once that message has been acknowledged, it basically unbuffers the message, and it also tells the producer controller, you no longer need to buffer this message either. The producer controller will back pressure the producer when buffers are full. This is its way of saying we've reached peak capacity. And basically the producer kind of needs to use a little bit of behavior switching, where if I don't have demand for the producer controller, I can't send it work because the producer controller will crash. That's how it's going to respond if I don't obey the protocol. And that'll show up in your logs, and it'll be very clear why that happened. So you need to use maybe a little bit of behavior switching to go ahead and basically stop producing messages when you don't have demand. The producer controller does have a buffer, so it will run a little bit further ahead of where the consumer controller is. So it's not one-to-one. You do get a little bit of slack inside the system, essentially. On top of that, the producer controller optionally has the ability to persist its delivery buffer state using Akka.Persistence under the covers. We'll see an example of that too. The consumer controller, kind of already described this a little bit. It's on the receiver side. It basically maintains a sorted buffer of unprocessed messages. It keeps track of which messages have been acknowledged by the consumer. Basically, it forces the consumer to move through those messages in order. That way we don't end up delivering messages out of order to the consumer. Akka.Delivery basically maintains exactly once delivery with message order preserved. Now there is one edge case where we can accidentally have a duplicate. It's actually an edge case of an edge case, so it's very unlikely to happen. But I will talk about that a little bit later, since if you're a production user of the system, these are things you should be aware of. But by and large, by default, the system is very reliable and fairly hands-off for end users. The other thing that the consumer controller will do is it basically just kind of tells the producer controller which messages have been consumed, which ones haven't. Now, the first thing we have to do to kind of get the Akka delivery system squared away is registration. This is where the producer and the consumer need to register with their respective controller actors. So I need to send a start message to the producer controller. I also need to send a start message to the consumer controller. And then finally, the consumer controller and the producer controller have to get registered with each other in order for message production to begin. So there's two ways you can do that. You can tell the consumer controller, register to producer controller. That'll cause it to send a registration message over the wire. Optionally, if the producer already has, or maybe some other actor has a reference to the consumer controller, you can just send this register method directly to the producer controller. And that'll go ahead and cause it to get registered as well. So once all this is done, this is all that we need to go ahead and actually begin message production. So the message production process happens immediately after registration. Basically what the producer controller will do is it'll tell the producer this request next message. This is our way of signaling that there is demand for additional messages. So when you get that request next message, that means that there is demand available and you can reply back with exactly one message of type T. If T is an interface, this can be any message that implements that interface. You send that message to the producer controller will sequence it and deliver that message over the wire, and the consumer controller will deliver that message to the consumer, assuming that this message is at the front of the delivery buffer. If there's other messages that have already been delivered previously that the consumer hasn't processed yet, those will get delivered first. On the message consumption side, the consumer needs to reply back to the consumer controller with a confirmed message. This basically marks the message at the front of the delivery queue as successfully processed, and the consumer controller will then deliver the next message in the buffer to it. Simultaneously, the consumer controller will send a request message back to the producer indicating, hey, my consumer has moved this far through the sequencing process, and the producer controller will acknowledge that. It'll purge any buffered messages it's previously stored. And if we're using persistence, we'll go ahead and mark those messages as confirmed, which will result in us deleting them from our journal eventually. And then we'll go ahead and send some more demand to the producer. So you are not being back pressured if you're the producer anytime you get the request next message. This means there's demand available. So as long as you have an active request next message you've received, you can continue to send messages back to the producer controller. The next thing we'll take a look at is message chunking. What do we do with really large messages? This is sort of what the configuration looks like for chunking a large message here. So I haven't shown any code yet for the producer consumer controllers, but this is what it looks like. We're going to create a producer controller settings class right here. This is a C# record type. It's the first time we've used these in Akka.net so far. We're going to go ahead and say, you know what? We're going to take the default producer controller settings from Hocon, but we're going to modify it. So we're going to chunk messages into 64 kilobit slices. And then we're going to create some props for our producer controller. We're going to specify the type of message that we're going to use for it right here. We're going to pass in our producer ID, which got passed into this function here. And then we'll go ahead, start the producer controller, and then we'll tell the producer controller to register the consumer. And we'll go ahead and actually start production by registering the producer with the producer controller. All right, so this should go ahead and get everything started. Now, what the message chunking process looks like is when we go ahead and receive our request next and we reply back with a message of type T, let's say for argument's sake, we're using 100 kilobit chunks rather than 64K, just easier to reason about, powers of 10. We're going to go ahead and say, all right, if this message, after we serialize it, is a 400 kilobit byte array, we're going to break this up into 100 kilobit chunks, 4 of them. We're going to begin delivering sequence messages. We're going to assign a unique sequence number to each of these chunks, and we indicate which chunk is the first in the series, which one's the last. You don't need to worry about this. This is all handled internally by Akka.Delivery. But we're going to stream these chunks over the wire. And once all of the chunks have been received by the consumer controller, we're going to go ahead and deliver that chunked message. We're going to deserialize it and turn it back into its original format. And we're going to deliver that to the consumer. When the consumer replies back with a confirmation message for that, we're going to send a request back to the producer controller, who will in turn mark all those chunks as delivered and then send more demand back to the producer. And this happens somewhat transparently behind the scenes. In fact, we're going to do a little demo right now where I'm actually using a chunked producer, and we're going to see that the fact that we're chunking or not has zero bearing on any of my code I write myself when I'm working with this feature. So we'll go ahead and jump to that. Okay, so for our demo, I'm using out of the Akka.NET Code Samples repository, and I'll link to this in the notes. We're using the SQL sharding plus Razor Pages example here. So we're using Akka.Cluster sharding with SQL Server behind the scenes and ASP.NET 6 with Akka.Cluster sharding enabled. So I've already got my application running right here, and basically the way this works is I have a bunch of different sharded entity actors. I've kind of pre-populated about 7 different entities here. These are just different types of bourbons. And if I click on one of these, this will allow me to load an individual little entity actor right here. I'm basically querying this data directly from a cluster sharded actor rendering on screen. But whenever I go ahead and I load the index here, this is actually being served up with message chunking via Akka.Delivery. And the reason why we're doing that right here is when I actually have a huge number of products that are getting sent over the wire, it all comes as one message, which gets serialized into a protobuf object. And if I have enough products available, let's say I have several thousand of them, that message will be bigger than the default frame size that Akka.Remote supports. So message chunking might be an attractive option here. So let's take a look at how we actually go about configuring that. So first things first, I have 2 different processes. I've got my SQL sharding host and my SQL sharding web application. So my host is going to be where my data comes from. My web app is going to be what consumes that data. So if we take a look at our various actors here, this is on my host. This is where we produce data. I have my shard region where all my little product totals actors live. These just keep track of all the orders and shipments for a specific product. But then down here, I have my singleton, my product index actor. This is going to be the actor that sends back the big responses that the index page of my website really wants to have. So if we scroll down here, we'll go ahead and see that we have, lo and behold, a ProducerController.requestNext message for the fetch all products protocol. Now, if I F12 into this is an example of kind of building a message protocol together. Basically what I'm doing is saying, okay, for this particular type of query, there's really only one message that we're super interested in, which is that we want to go ahead and support, if I take a look at the inheritor, it's the fetch all products response. This is going to basically be just a list of product data messages right here. So our protocols at this rate kind of just limited to a single message. If we supported, let's say, a more diverse array of queries, we would probably have several that all implement this interface here. So this is kind of our typed protocol. Now, when I get this request next right here that comes in, I am basically going to signal for this particular producer that demand's available. One of the things I'm doing here, because this is a cluster singleton actor, is I'm going to spawn a producer controller for every single request I get, because there's only one copy of this product index actor throughout the entire cluster. So if I've got 100 web nodes, I've got 100 consumers who all want data from this one actor. So I'm going to spawn a producer controller per request. So what's going to happen is that when I receive a fetch all products message right here, I'm going to hit F12. I'm going to see if we already have a producer controller registered for this particular producer ID. And this producer ID is generated by the client in this case. This is a message that's just sent to us via Akka.Remote. And if we have a producer controller that's already available, I'm going to check to see if we have demand. If we do have demand, we'll just go ahead and send our message to the producer controller and it'll do its thing. And we'll signal that we've met demand for now. And we'll go ahead and cancel any redelivery or retry timer that we have. Otherwise, if we don't have demand, we'll go ahead and schedule a retry for this request 1 second in the future. And we'll do a little bit of exponential back off by just bumping up our attempt count here. This code's all open source. If you want to look at it, you can go ahead and kick the tires on it yourself. This is where things get more interesting, which is that if we need to start a producer controller in order to service this brand new unique consumer, we'll go ahead and take the producer ID and the reference to the consumer controller actor and call this create producer controller method. And this is the exact same code you just saw on screen on my PowerPoint slide not that long ago, where I'm going to go and create my producer controller settings. In this case, I'm going to use 124-bit chunks, so 1 kilobit. And we're going to go ahead and create our producer controller right here. So I'm going to pass in the producer ID. We're not going to use the durable delivery queue for this one. And we're going to pass in our producer controller settings. That way we can force chunking. We'll go and start our producer controller here. We'll register the consumer with it. And then we'll go ahead and start production. This is all the messaging we need to do in order to actually begin message production. Now let's flip over to the consumer. This is my web application. So this is a .NET 6 minimal web API type deal. I'm going Akka hosting right here, so I'm starting my actor system. I'm going to start a cluster singleton proxy. This is going to point to that cluster singleton actor, the product index actor over here. So I'm configuring that. And then I'm going to call this method down here with actors. I'm going to go ahead and use the dependency injection resolver to create a brand new fetch all products consumer right here. This is going to be an actor that our web UI is going to talk to. And I'm going to go ahead and start this actor. And let's take a look at it. This fetch all products consumer is basically, there's one of these per instance of my web front end inside my application. This is a Razor Pages app. The index page talks to this actor every time it needs to resolve its index. So what I'm going to do is I'm going to create a brand new producer ID by just creating a GUID and sticking it in here. That way it'll be globally unique for this node. If this node restarts, it's going to lose all of its request state anyway. We don't really care about making this ID persistent or sticky. Another approach to making this work, which I did in one of our code samples, is I could go ahead and get access to the cluster's address and hash it and use that as the producer ID here. And that would also give me kind of a URI-friendly producer ID if I wanted to do that. Next, I'm going to create my consumer controller settings. I don't need to do anything special here. I'm just using the defaults from Akka.net. But then I'm going to call ConsumerController.create, and I'm going to pass in the exact same message type that my producer also uses, the iFetchAllProducts protocol. This is defined in a shared library, as your messages usually are. So I'm going to start this actor up. I'm going to go ahead and allocate it here, and then I'm going to register the producer with this actor. In this case, the consumer is actually starting the consumer controller. That's pretty common, so there's nothing wrong with doing that. So I'm going to go ahead and start message production here. And lo and behold, if I scroll down, if I receive a fetch all products query, this comes directly from Razor Pages, I'm going to tell the product index proxy this little fetch all products impl, and I'm going to pass in my producer ID and a reference to my consumer controller. And I'm going to shift behaviors and become waiting for response. And I'm going to set a little timer here that's going to time out this request. And lo and behold, if I get a ConsumerController.delivery for fetch all products, I'm going to go ahead and use a little bit of pattern matching here. I'm going to grab the response, and I'm going to tell the consumer controller that we are going to mark this message as consumed. And then we'll go ahead and deliver this to our little requester. This is going to be usually a ask actor that's being called from inside our web app. And then we'll shift our behavior back to this state again, start the process all over again. All of my messages are being chunked. They're all being reassembled on the other side of the network. And all I've really kind of had to do from a management standpoint is I did have to add a little bit of code to my cluster singleton to make sure that there was a producer controller made available for each unique requester. It's one thing I did need to do. The Akka.cluster sharding version of this, which we're working on a video for that next, actually automates this for you across a sharded sort of shard region. So you don't need to actually manage the spawning of consumer and producer controllers yourself. That's all kind of built in. For managing this one-to-one and doing things like message chunking, I just had to build a little bit of infrastructure for that. Otherwise, I just needed to pass in a unique producer ID and a little bit of work to kind of connect the consumer producer controller together, and otherwise everything runs automatically. This code is actually a lot simpler and ultimately a lot more reliable and a lot more effective than what we were doing with things like Akka.Persistence's at least once delivery actor before. And on top of that, if you have Akka.Persistence enabled, you can make this whole system durable so that in the event that I had to reboot my process that has a producer running on it, I can go and recover all that data and redeliver it to my consumer. And I'm going to show you how to do that next. So obviously one of the things we need to do in order to help make the Akka delivery system reliable is we need to have a means of making the producer controller's data persistent. And that's what the EventSourcedProducerQueue does. This is an optional setting you can pass into the ProducerController.create method, which will make it such that all of the outbound delivery buffer data all gets persisted using the Akka.Persistence journal and snapshot store, which also means you as the end user need to have one of those configured. Most people who are using Akka.cluster and cluster sharding are already typically using one. So here's what else you can do that's kind of interesting. The producer controller sends you a request next message, and there's a method on it called askNext2, which will allow you to pass in a message with confirmation. If you pass in a message with confirmation and type T into that method, you will get a task you can wait on, which will return a 64-bit long integer, so long type. This task will complete when the producer controller successfully persists that message into the buffer, meaning that the message is persisted now and it's not going to get lost even across restarts. And the number you get back is the sequence number that was assigned. So if you are really focused on trying to make sure you have reliable delivery across all scenarios, that would be a really good idea to actually take advantage of that. That way you can confirm the message has been persisted. It's kind of like an outbox pattern. I know it's going to be delivered now, and there's no chance of it being lost. And here's what configuring the durable queue looks like. Basically, we need to reference Akka.Persistence naturally, and we need to use this EventSourcedProducerQueue.Create, and we type it with the same protocol that the producer and consumer controller are going to use, and then we have to give it a unique unique persistence ID. So that's what we're doing right here. And then we just pass in the prompts that you get out of this create method right here into the ProducerController.create method. And that'll go ahead and cause the producer controller to persist all of its delivery data and all of its confirmations as they come in. And this system will kind of self-manage its snapshots and its usage of the journal to make sure there's not too much data kind of lying around at any given time. So it's pretty efficient about managing that. All this is also customizable inside Akka.Delivery as well. You can go ahead and say, I want this thing to save a snapshot every 100 messages, and that way it'll delete all that data that's sitting inside the journal. Last couple of notes I'll mention in this video about Akka.Delivery. The first is that the producer and consumer controller are designed to survive the other one restarting. We have built-in restart detection for both of these, and we have numerous unit tests that all ensure that in the event that, let's say, a node that we had a consumer controller on, let's say it shuts down and that actor gets started up somewhere else, that actor can connect back to the same producer controller and not miss a beat. We totally support that, and the vice versa is also true. The one thing that is noted is that when a producer controller restarts, the sequence number will reset back to 1 unless it's durable. If the producer controller is durable, it'll resume delivery with the oldest unconfirmed message. We preserve message order across restarts as well. So if you're using that event source producer queue, we'll go ahead and take the message off the front of that queue and begin redelivery with that right away when we start up. Now, here's that one edge case of an edge case I mentioned where you can get a duplicate. Imagine you're a producer controller and a consumer controller up and running. The consumer controller has received a buffer of messages that it's handing down to the consumer. And then the producer controller, who is durable in this case, so it's persisting its data, crashes and restarts. Well, in the event that there are messages being confirmed on the consumer controller after the producer controller is in the middle of its, let's say, not just restarting, by the way, it's actually being terminated and recreated. So that actor has been completely shut down and recreated somewhere else in the network. During that stretch of time, the messages that have been confirmed by the consumer controller, those confirmations won't make it back to the producer controller. And that's the one scenario where a duplicate can occur. It should be relatively easy to detect because the first new messages that you'll get from the producer controller will be messages that are older than the previous sequence number that you've processed. That delivery message the consumer gets includes the sequence number. You could very easily go ahead and check that. As long as the sequence number is not equal to 1, if the sequence number is equal to 1, that means we have a brand new producer controller that is starting from the very beginning and it has no durable state. That's what that means. But if it's a sequence number of, let's say, 2 or higher, then you know that you're in this scenario here, and you can potentially just save that long integer in your consumer and check it that way. If the producer dies, nothing happens. The producer controller will just wait for another actor to respond or request next message. You can just send the producer controller a new start message and re-begin the registration process. However, if the producer sends a message to a producer controller when there's no demand, the producer controller will die. If the durable queue dies, the producer controller will restart and recreate it. We have the ability to tolerate that in the event the Akka.Persistence has an issue. If the consumer dies, the consumer controller dies. These two have a very tight relationship. So if the consumer shuts down, the consumer controller will also shut down. So that'll do it for this video. If you have any questions about Akka.Delivery, please go ahead and leave them in the comments. We'll make our next video all about Akka.Cluster sharding and how to use Akka.Delivery over that. But otherwise, thank you very much for your time. We really appreciate it.